Newton Raphson method. So find the root of the equation f of x. Also we say begin equation which is x to the power Okay, so that's what you're doing. So in this case, we want to use the Newton Raphson method, and the Newton Raphson method is offered in scipy under what's referred to as the Newton. Okay, so the Newton function. So we're going to do an import. We're going to say import Newton. Newton function from scipy.optimize submodule. So from scipy scipy.optimize import Newton. Then next we can get help on Newton. Get help on so say do that. We get a small description of what the function does. So here it says help on function Newton in model scipy that optimize zeros. So basically, here it says, what does this function do? Find a zero of a real or complex function using the Newton Raphson or second or high list method. So basically, there are three methods. The same function can be used to do three different things. So the first one is the Newton Raphson method. The other one is the second method. Then there's something called Halley's method. This one here. Our interest at the moment is how do we use this function to do the Newton Raphson method. Now, for us to do the Newton Raphson method, we are going to need a function. So we're going to need a function f of x, func. Then we're going to need a starting position, x prime, x naught. Then you're going to need f prime. F prime is the derivative of the function which we are interested in. Okay. Then of course there's other things that have already been said. For example, the tolerance, which is between the roots, the maximum number of iteration. This also has been set. Maximum number of iteration has been set to 50. If you remember, for the bisection, the maximum number of iteration was set to 100. So basically, with what already you can see that with this particular method, we maximum for you to get a where it has been set to 50, trying to show you that actually this method is much faster. There's this other bit here, f prime, second f prime. For this second f prime, I think this is for some other method. Then if we needed to do the second method, we would need this x1. So if we were doing second, we would need this other method value of x1. So for second method, you would need x0. Then you would not need this, but you would need to supply x1. So the same Newton method, the same Newton function can do both Newton Raphson method and second method depending on what kind of information you provide. If you provide the function, the name of the function, you provide x0 and you provide the derivative of x0, then in that case you're going to be doing the Newton Raphson method, which is what we want to do this afternoon. If on the other hand you want to do the second method, then you provide the name of the function, then you provide x0. You would not provide this, but you would provide x1. If you provide x1, then it would do the different method, which is the second method. The other method, which is Halley's method, I think probably this one we'll probably look at it when you guys reach fourth year. For now, we're not looking at this. We're just looking at the two of them, Newton Raphson method and the second method. Okay. Then down here you've got a few descriptions of what stuff is. So parameters, the func, see, that is a function. X0 is your what's this? Your guess value you're starting with. F prime is the derivative of the function. Of course, the tau is the tolerance. What else? Maximum number of iterations. Then this other bit here is f prime 2. F prime 2 is what you would need according to what we're being told here. F prime 2 is the second order derivative of the function when available and convenient. If it is none, so if you don't have the second order derivative, then the normal Newton Raphson method or the second method is used. But if you provide the second order derivative of a function, then this method is carried out. Halley's method is used. Are we clear? So this other method with which our Newton Raphson method can do, if you can work out a second order derivative for that particular function, then this other method is carried out. But for now, we are not looking at this other method here. For now, I will look at the documentation and see how it's carried out if there is need for us to actually do that. Okay. So what else are you going to get in return? You get a root, then you also get some stuff on whether things have converged or not. Yeah, so basically that should be that. So the first thing we need to do is we need a function, then we need to provide a function, we need to create a function, then we need to supply a value of x of x naught. We also need to supply a derivative. Okay, so for our example, our function is this. Now this function, I think we already created that, but you're going to do it again. So here I would say create. Just a minute, I'll copy that. You don't need to create something entirely from scratch. If I can copy something. Okay, create the function x to the power 5. Then you have 2 minus 2 x to the power 2 minus 3. X to the power 2 minus 3 equals to 0. So in this case, we will create this lambda first. So we're going to say f lambda. Then how many variables does the function have? It only has 1. Then what's the expression for the function? That's x to the power 5 minus 2 times x to the power 2 minus 3. So that's what we have. So that is our function. Okay. Next bit, we're going to create the derivative of this guy. Because we need a derivative. Create a lambda function for this guy. So the derivative of this function, which is the f, that's going to be 5 x to the power 4, then I think 4, then this bit is going to be 0. What do we have? Or let's say the f prime. Yeah, so that's going to be the derivative. So when you create the lambda for this derivative, so our derivative, we're going to call it the f. The f is going to be equals to lambda, then the variable, the expression for the lambda, that's going to be 5 times x to the power 4 minus 4 times x. If you want a plot of these functions, that's okay. We can, I think we have some expression for the plots at the beginning. What did you have? X range. You can get this. Just a minute. So we want to see how our function looks like, and also we want to see what the derivative of this particular function, how it behaves. Okay. Just a minute. Since we already did this earlier, most of the stuff we're just doing a copy. Okay. Print x. So that's what we have for x. The other bits is us printing the value of the function and also printing the value of the derivative. Okay, so here so print f of x, print f of x, the value of the function, that's what you have. Then also print the value of the derivative, so we can we're sure that these things are working as expected. The value of the derivative, so that's going to be print the f x. Okay, so we're with the function printed out and the stuff like that. Then we can make a plot to see how these things are behaving. Where is it? Yeah, we'll get that. Okay, yeah. So here we're going to say make a plot make a plot, a simple line plot of f of x and the derivative f prime of x. So here this is our plot of f of x. So you do those plots. All right, then the other bits is PLT dot plot. So we're saying x the f prime. We are saying plot of the f. So in the legend we have this guy, So the first one is for f prime of x. The second one is we will do that f prime that's one f prime of x, that is equals to, I think, 4x to the power 5x to the power 4 minus 4x. So this bit we can do that and try to make a plot. So that's what we get. So the first one, oh no, something has changed just a bit. The other one is this here is supposed to be x to the power 5 minus 2x to the power 2 minus 3. Okay, so that's what we have. So the blue one, that's how the function itself, f of x, varies with x. The other one, the other colored one, the orange one, or the orange one, that is the derivative of the function. So for you to use Newton Raphson method, you always have to make sure that you can easily work out the derivative for this particular thing which you are this particular particular problem which you're working out. So in our case here, so this is example number what example are we looking at? That's example number 3. So we can change here there. I say, okay, this is for example number 3. Then I can save this plot. Okay, so we have our derivative which works, we are with the function which works. Are we clear so far? Is it clear? Hello?
Yes, it's clear.
Okay, so next we use the Newton Raphson method. So in this case, call the Newton. We're going to make a call to the Newton function. Call the Newton function. Newton function with function f of x, first derivative the f of x, and starting value x set to x0 set to 2. So we're going to say Newton, then func. The func is f, that's our function. Then our x value, which is x0, x0, or x0 is being set to 2, and our f prime, the first derivative, which is f prime, that is being set to df. With that, we can run this, and we get our answer as 1.495106 397623 22616. Are we clear?
Yes, not clear.
If you want more information about how many times and everything else this function runs, you can of course always set there's a parameter. If you go to our help, there's this parameter here. If you go to the help for the Newton Raphson method, there is this parameter, full output. You set your full output to true. If you set your full output to true, then you can get information about how many times and everything else this thing ran. So in that case, we can do that. If we do that, we're going to say full output, set it to true. If we do that, we get more information. So we get our root is this much. And how many iterations happened? Only 6. Compare that to what we had for bisection. The same function for bisection, if I recall very well, for bisection, the same function we had. Which one is this? Not this one. The previous one. Yes, for bisection, this same function, example number 1, for bisection, the number of times it ran was 40 for us to get the same kind of answer. So for bisection, it ran 40 times, but for this same function, when it comes to the Newton Raphson method, it only runs, if I'm not mistaken, what I saw there was 6. Yeah, here. 6 times. So, you can see that the Newton Raphson method is faster than bisection, as is always the case with open methods. Open methods are usually faster than bracketing methods. But of course, sometimes your answer can converge. Other times, your answer might not converge if your function behaves in a funny way, and also if your starting value which you have chosen is not nice. Then you might end up you might get yourself in a bit of trouble. Are we clear on how you would use the Newton function, which is in scipy.optimize, to work out your root using the Newton Raphson method? You need to provide the function, you need to provide the starting value, you also need to provide the derivative, the first prime of the function. Are we clear?
Yes, we are very clear.
Okay. The other example, which is in our notes, is this one. So here, example number 4. Find the root of the equation. Okay, that. x to the power 2 minus 2x minus 1 equals to 0. So basically, with the Newton Raphson method, starting with that bit, so I think part of this function has been done, if I'm not mistaken. Yeah, part of this function has been done. So the only thing we need to do is we need to work out the derivative. So you need to do a print. Yeah. Print numpy array x. So that's our array x. Then we create this lambda for a quadratic function. We need to move this a bit down. So the lambda for a quadratic function, we have what it only takes one variable x. Then we would, that's what you have here. So we say we make an f, then it takes one variable x. Then the rest of the expression is this one, x to the power 2 minus 2x minus 1, which is what you have there. So that is the lambda for our expression. Then you can work out the values of x at this particular, that's what you have there. Then we also need to create the lambda for the derivative of this particular function. So create a lambda for f prime. So f prime, so that's going to be 2x minus 2. That's going to be the derivative. F prime is going to be 2x minus 2. So in that case, we're going to end up having the f is going to be lambda x 2x minus 2. Then you can work out what the values of the function are going to be. At f prime. So you can do a print print the f prime. Okay, there, so their values. Then you can make a line plot like we did. Of that and that. So in that case, we're going to add another thing here, another plot for the derivative. The plot x dfx. Then inside here, that's the first one. Then the second one belongs to the derivative. So you're going to say f prime f prime x is going to be equals to 2x minus 2. So when you do that, this is what you have. So this is our function f of x. Then our derivative is just a straight line. The derivative of a quadratic is always a straight line. So this is our straight line. That's a derivative. So you can see all throughout this between 0 and 1 and 4, you have your function has got values there. Okay. So with this information, we can now work out what is the value of the function at that particular thing which you have. So where did we? Yeah, so here. So we call the function. Now we are starting with x naught equals to, what do you have for x naught? 3.5. Yeah. .5. So Newton function is f. Our x naught is 3.5. Then our derivative f prime. Our f prime is the f. So we run that, we get our answer as 2.41 that bit. You want more information about how many times this whole thing runs, so you can set your full output, set it to true, then you get more information about how many times our thing runs. So basically it runs 5 times. So this is us without laboring so much. This is us using Python code which already comes with what we're using. In this case, we're using Anaconda, and Anaconda supports modules like scipy, and scipy is the module of choice for physics people who are trying to do computational stuff. Very, very good for computational physics. So I would encourage people to, if you have to watch up some videos on YouTube, look up a video on scipy, watch and see how people are doing things. What I'm teaching you is not the only things you can do. There's so much more out there which you can do with scipy. Okay. But of course you've got a syllabus to follow, and you've got things which you need to do, and we are trying to show how we can do that. So basically this is the smart way of doing things. You see what functions are available, what do they do, how do they do things, then off you go, you find your stuff. Any questions?
No question from me.
Is it clear? The other people? Are we clear? If you've got a question, you ask now. If you don't have, then fine. Say you're okay, then we close up this thing. When we meet on, so our next class is going to be on Thursday. So when you meet on Thursday, we are going to see how to use the same Newton function, but now to do second. Remember, there's a second method which we learned how to do. Now the same Newton function can do 3 things. It can do Newton Raphson method. It can do the second method. It can also do what's known as Halley's method. So what we have looked at is only bisection, Newton, and secant. These three methods for now. So that's what we're going to see how to use it for. We're going to use it only for the Newton Raphson method and for the secant method. Okay, so if there are no questions, we end here. So we're going to meet on Thursday, same time. Hopefully we can get rid of this, how to work out things with the computer, this bit. Okay, so hopefully this week, after Thursday, Thursday we have 1 hour 30, then we're going to Friday class. So hopefully this week, the first hour we can use it on the secant method. Then the second time, I think we can look at a bisection we can create ourselves, or which we created last year for the other your friends who are already in 4th year. So we can look at that and how it works. Then on Friday we can probably look at how you could create from scratch your own Newton Raphson method, your own secant method. But with this already there, it's basically probably trying to see how you can do stuff on your own if you don't know if that there's a particular solution which is available. But I think, yeah, so basically that's the approach we're going to do. We'll be seeing how do you do something with a solution which is there. Then later on, if we can try to implement the same solution on our own and see if we get answers which are comparable. Okay. So if there are no other solutions, no other questions, we end here. We're going to meet on Thursday, same time. All right, so see you on Thursday.